Good morning, class. We're about to record another lecture on the steam power plants class. Excuse me, I just finished breakfast here. I'm choking up a little bit. I hope everyone's feeling well this morning, and we'll get this one posted along with a video I want you to watch on wastewater associated with steam power plants and coal boilers. It's pretty interesting. Okay, so the last video I had you listen to that you have a quiz on today from 2 to 2:30 on iLearn was pretty good on the boiler fundamentals, and he covered a lot of things that I usually talk about. So I discovered that, thought it was pretty good. So I figured I'd let you listen to him instead of me all of the time. I know you love these little recordings, but nonetheless. Okay, but I'm going to give my kind of general boiler fundamental overview as we talk through some of these handouts that I think I've already given you, and I can certainly email this out again to you if you can't find it. But this is, I think, this page 2 of this 12-page deal. Let me make this just a little smaller here so we can get it all on the same. There we go. Okay. So I'm going to talk through this utility scale pulverized coal boiler and just make some comments. I guess a lot of this will be similar to that last video, but a little going back and hearing it a second time is not necessarily terrible for you. You'll notice that the overall boiler is divided into the furnace section and the convection pass. So I think we know by now where the furnace is. This is lined by the water wall tubes. Burners fire the pulverized coal and hot air mixture out into this to establish the fireball. This is where the steam is generated inside these tubes. This is a drum boiler. We're showing a steam drum up at the top of it. And then the hot gases from the leave the furnace and travel horizontally through the convection pass, and then down vertically down, and eventually go through an air preheater where the forced draft fan is blowing combustion air that's going to come into the boiler on one side of this air heater, and the hot flue gases go on the other side, and then they are sucked out by the induced draft fan. They go onto the various gas cleanup devices, electrostatic precipitator, scrubber. If we're doing NOx removal, it actually would be shown up in here before the air preheater. So this particular slide doesn't show NOx removal. Okay. So let's see. Let's follow the water path here a little bit. So water comes, as we recall from our Rankine cycle review, we have numerous feed water heaters in the steam cycle. That's part of the regeneration. We're going to transfer heat, take extractions out of the turbine into the feed water heaters, preheat the feed water before it gets back to the boiler. So at the exit of the last feed water heater, we're still pretty hot. I can't remember the number on Kingston, but it's probably 350, something like that, Fahrenheit, roughly, give or take a little bit. And we're going to come over here to the economizer, which you'll see on the left-hand side. And that is, excluding the air heater, that is the last heat transfer section that the flue gases see before the air heater. And so that is just one more stage of feed water heating. So it enters the boiler, goes through the economizer, and then the feed water goes to the steam drum, where it actually, I guess you could say, enters the boiler formally, even though the economizer is part of the boiler as well. At any rate, so we pick up probably 40, 50 degrees of additional temperature in the economizer. We go up to the steam drum. From the steam drum, we flow downward through the downcomer, which I believe is this pipe. I don't know if you can see the arrow, but there's pipe coming out of the bottom of the steam drum. I think what they're showing is the downcomer, even though they don't tag it as such, down to the bottom of the boiler where it enters the distribution headers that feed all of the individual water wall tubes. Okay, so this, the water in the downcomer is relatively cool compared to what goes on inside the water wall tubes, and so that establishes this density difference between the downward leg and the upward leg through the water wall tubes that causes a natural circulation. If it is a forced draft boiler, it'll also have a pump, a boiler recirculating pump that will be pushing the water along this path. If it's a natural circulation boiler, it's all done with density gradients. I mean, there's a density difference one way or the other. It's just whether or not we happen to have a pump to pump through, make the circulation more predictable and perhaps a little faster. Okay, so then inside the water wall tubes, we receive mostly radiant heat, a little bit of convective heat, but mostly radiant heat transfer in the furnace. We vaporize or boil off a portion of the water from the water wall tubes, probably on the order of 3 to 15% is typical, and then maybe 3 to 20%, and then that mixture will go up to the top of the boiler. There's another header that collects all of that, takes it back to the steam drum, where we have the separators and the other components that were listed in greater detail in that previous video. So the steam separators will separate the liquid water from the steam, and hopefully we have dry steam then leaving the drum, and it then is transferred via pipes over to the primary superheater. So this is the kind of the order, as so we come out, the steam comes out of the drum to the primary superheater, flows through here, is preheated, and this is a relatively cool section of the boiler compared to what comes out of the furnace. And then we exit the primary superheater, we go to the secondary superheater, and in between we have a temperator, or a temperator which can control the steam temperature by spraying small droplets of water that evaporate into the steam flow, and that evaporation process will cool the steam some, and so that gives us a very quick, almost instantaneous adjustment on steam temperature. We have some other means of adjusting steam temperature that we'll talk about a little bit later. Okay, so we come out of the primary superheater, past the temperator for adjustment, then we go into the secondary superheater where we get additional heat added, and then we go out, exit the boiler, and go to the high pressure turbine. So that's kind of the order of things on the steam side. After we have expanded through the high pressure section of the turbine, then we exit there, and before we go into the medium pressure turbine, we come back to the reheat superheater, which you see, which is kind of, it's the flue gases hit it after the secondary superheater, but before the primary superheater. And so the steam is then reheated, and then it exits there and goes back to the intermediate pressure or the medium pressure turbine, expands through there, and then goes straight through the low pressure turbine sections, then to the economizer. Of course, we have extractions from the various steam turbines as the cycle is designed. We're showing up in the upper section here in the center, typical soot blower locations. So this pulverized coal, each little, which is the consistency roughly face powder, each little particle is a little chunk of coal. It has gases that volatilize or come out upon heating, which are very combustible. They burn readily. it leaves kind of a carbon-based particle that also has ash and other mineral constituents in it. The carbon takes a little longer to burn out. Hopefully we have enough residence time at high enough temperature to burn all of the carbon so that it doesn't wind up as LOI, loss of ignition, in the ash, which the LOI reading is, you know, a percent of the ash that is still carbon, meaning that we didn't burn it all in the furnace, which of course is a loss to the system. As we look down, just look at the diagram here, we see the fans down here on the bottom right. We've got the forced draft fan. So that's just bringing ambient air. Actually, come to think about it, that air is pulled from the top of the boiler house. Because if you've ever been in a boiler house, especially in the summertime, you realize that all of the heat losses from the furnace itself and the hot components, that heat is inside the building. It rises up to the top floor readily, and it may be 95 degrees outside, but it'll be 135, 140 up at the top of the highest level of the boiler house. And so if we pull this forced draft air from that, we're recovering some of that heat that was lost from the shell of the boiler, and we can put it back in the furnace. So that's what happens. That's where the air is pulled from. You want the warmest air possible because that's going to improve your efficiency a little bit. So we're going to pull off of the top of the boiler house. We're going to pull air into the FD fan, and it'll go through the air heater, and then it will split. Some of it will go to the pulverizer, and then in the primary air fan, and then transport the pulverized coal particles from the pulverizer through the coal pipes to the burners where they are burned. The rest of the air from the FD fan, it becomes secondary air and goes to the wind box, and then, which is our chambers around the outside of the boiler that are pressurized, and that air, that hot air, is then forced at various locations into the boiler to stage the combustion a little bit, to try to minimize the flame temperature a little bit and reduce the NOx emissions. Okay, over on the left-hand side, we see the coal bunker. So, you know, we have the coal pile outside. So the coal comes in on rail cars. It goes through a crusher, which crushes it to basically, you know, 1 to 2 inch chunks or smaller. It's then transported via conveyor up to the top of the boiler house, and then the various coal bunkers. Each unit at Kingston, there's 9 units. Each unit has its own coal bunker, and there's a conveyor up there that can fill each of those bunkers with probably 2 days worth of coal supply. And so they try to keep those bunkers appropriately filled. The coal then falls down from the bunker they typically have scales that will weigh this coal, and then it fills up as we need to supply coal to the pulverizers. The coal falls from the bunker onto the coal scales where the weight is measured automatically, and then it goes on to the pulverizers where it is pulverized. It's then transported by this very warm to hot air mixture through the coal pipes to the burners where the fireball is up and going, and then the primary air and the coal particles are blown out into the furnace, into the region of the fireball, and then they sustain the combustion in the fireball. I'm going to go to another. This was something I found online. Let me make this a little bit bigger. There we go. So this shows a pulverizer, simplified pulverizer process. And so I just thought this a little more detail than I've got on the other one. So we see the bunker feeding the coal feeder, feeding the pulverizer. And we have a cold air feed and a hot air feed. The hot air would be air that has gone through the air preheater, and they are blended to maintain the desired temperature of the air and the flow through the pulverizer. Then this is showing an exhauster fan, um, which exhausts the pulverizer, which then goes through the coal pipes into the burners. Over here, we're showing secondary and tertiary air, which is heated air, again, to stage the combustion. And we're coming out, the flue gases come out the top here, bag house for gas cleanup, and lots of other stuff in there. Okay, so back over to this diagram. Let's see, what else do we need to talk about here? We see the coal bunker burners, coal feeder, the coal pipes you can see going to the individual burners. You've got a primary air duct. That's what is feeding the air to the pulverizer, the hot air, and then there's could also be a cold air. So where there's going to be some blending. You don't want it too hot or you increase the fire potential. But that hot air transporting those coal particles, it tends to dry them out. If there's any water, if they're wet at all, then it'll vaporize the water and at least take that into the boiler as water vapor instead of liquid water. Down at the bottom of the boiler, we see an ash hopper. We get clinkers and stuff can fall off of the furnace. Down to the bottom, there's usually a little bit of water down there that kind of quenches them. Let's see, furnace, soot blowers, temperator, reheater, economizer, primary superheater, secondary air duct, air heater, tempering air duct, just another air duct in the boiler. We see the air heater itself, which is typically a rotary device. And then the flue gases are basically sucked out of the boiler by the ID or induced draft fan, which either draws them or blows them through the rest of the gas cleanup equipment before they are dismissed to the atmosphere. So I think that's a pretty good talk through this one. Let's scroll on down and see. This is Kingston. These are the small units. This is 1 through 4. So similar type devices. I talked through the other one. I don't know. They're all these diagrams are better at one thing than another. But anyway, you see the exhauster fans on the pulverizers, the FD fans, the ducts, economizer. This one's set up on the other side, economizer, superheater, reheaters. So after you look at this a little bit, they all start kind of looking pretty similar, to be honest with you. These are the larger units, 5 through 9. Pretty much the same thing. This shows, let me make this a little bit bigger so you might see it. This is a kind of an updated figure. This shows the gas cleanup equipment a little bit better. So you see, as we come out of the economizer, before we get to the air heater, we have the SCR, that is for a NOx removal. You need to do that at temperature. It seems like, the top of my head, I always forget this every year, but it's someplace between 750 kind of sticks in my head, but there's a temperature range. But you want it pretty hot in order, it's usually ammonia that gets injected. Ammonia will grab the NOx molecules and form a solid that then you can pull out in the precipitator. So we do that hot, then we go through the air heater. This is a rotary device that rotates around that typically that heats the, this is coming out on this side, this is coming in on this side, that then preheats the air that's going into the boiler for combustion. And we're showing a precipitator, or fabric filters, whatever you're using to get all of the particulates and ash out, that's collected. And then we show the ID fan. and then going through the wet flue gas desulfurization system, and then we go up the stack. So this takes out the sulfur and takes out some of the heavy metals as well. Note the location, this is interesting. Note the location of the ID fan. It's after the precipitator. So on units, I may get this backwards, but basically units 1 through 4 at Kingston are the smaller ones, and 5 through 9 are the larger ones. And I forget which one, but one group has the ID fan located here, which is where you want it because you clean up the gas before it goes through the fan. The other units have it before the precipitator, which is a terrible idea. And so all of those flue gas particles, or the ash particles in the flue gas, what I'm trying to say, go through that fan and they erode those fan blades. And just about every year they have to tear those fans down, and they put ceramic coatings, or not coatings, but ceramic little like tile that they put on those fan blades in order to keep them from being eaten alive. And they still have to replace the wheels every 2 or 3 years if they get much runtime on them. A terrible, I don't know how that, well, I do know how it happened. What happened is when these units were put in, they didn't even have precipitators. They were just blowing the ash, and it was totally unacceptable. So they came in, and when they retrofit, for some reason, they didn't want to move the fan on one series of units. And so the fans are dealing with the ash-laden flue gas, and it's a terrible maintenance issue. But anyway, this gives you some kind of an idea what the flow path would be. And I'll be sending out chapters that you can look at on detailed chapters on the cleanup of the gas. Okay, let's see. Let me make this a little smaller. Okay, so what this slide is just comparing the size for the same capacity of plant. Look how much larger the coal-fired unit has to be compared to the natural gas unit. And so what that's going to tell you is that gas-fired unit's not going to cost as much. And you've got all of the coal handling equipment, pulverizers and stuff like that, and all the maintenance expense. Back in the day when all these coal-fired plants were built, coal was so much cheaper than natural gas that it justified all of this additional expenditure. These days, not at all. Natural gas is on a par. If you buy it at the utility scale on a cost per million BTUs, it's on the same order of magnitude as coal. And so that's just another reason that you're probably not going to see the construction of coal-fired plants. All right, let's go back around, make it smaller. So this shows an industrial type boiler, which is considerably simpler. A lot of the same components, this would be for coal. We're showing feeders. We're still showing a pulverizer. We got the furnace. So we have not so much extra heat transfer surface. We don't have a reheater. We do have a small superheater section, which may or may not be there depending on the industry. We have a boiler bank, and this is additional steam generating tubes. We pick up an extra drum. This is the main steam drum, and this is called the mud drum down here. And again, this is just additional surface area to generate additional steam. It's after the superheater, but before the economizer. Okay, and now we have a tubular, different style of air heater coming out. After a forced draft fan. They're showing a bark spout where you could dump some waste wood into this thing if you wanted to, and the various fans. So over fire air would be used if you're burning wood or something like that typically. But you got your coal burners over here. And so anyway. kind of interesting. This slide is here just to look at these are headers, and let me make this bigger. It is a little bit interesting. These headers are huge. This is this is a large diameter. This might be 16 to 20 inch diameter with all these tubes, holes cut in order to connect into a central flow to either break that apart and feed the tubes, or it could be, this is showing outlet tubes, but you can have another header that has inlet tubes as well. So, but you can get cracking. And so tube welds can crack. You can get cracking, ligament cracking between these holes, and that's a big deal in a plant. So keeping your headers in good shape. I mean, you think about it, this thing can be as long as the boiler with hundreds upon hundreds of tubes. If you have to replace one of these guys, think of all of the work to cut all of those tubes, haul this thing, cut it at the top, all the supports, cut this thing up, haul it out, put a new one in, and weld it all up. You're talking probably a month to 2 months worth of work and countless millions of dollars. So, and these things are affected by thermal stresses, how quickly you put a unit online or do load changes. We'll talk more about that in the next block of the course. This shows typical header. What is this? Temperature variation in the header. And as you have, the greater the temperature variation, the greater the possibility in generating thermal stresses, which as you cycle up and down cause crack initiation, growth, and eventual cracking and failure. All right, let's rotate back and a little smaller. This is out of the steam book. It just shows for the different, I guess, size and sophistication of boilers, the different percent of heat absorbed by different sections. And let's see. So you can see up here, this would be reheating. Let's start at the high-end large boilers utility scale. So you see we have, this would be the reheater. This would be steam superheating, and this would be just vaporizing the steam from saturated liquid to saturated vapor, and this is water preheating. So you see, you know, a small package boiler, you do some preheating and you spend all the rest of your energy just making saturated steam. Process boilers, you still got to heat it. Saturated steam, you may do some superheating. Industrial power boiler, just a difference in distribution amongst the percents of heat transfer, and then the utility boiler. So that's of some interest. All right, let's see, counterclockwise. Okay, so I'm not going to spend a whole lot of time on this because that last video I think was excellent on it. Figure out the optimum size. There you go. So we got two types of boilers. On the left, under partial steam generation, that's obviously a drum boiler. And so you see, you have just almost a cartoon style, but you can see the heat input would be on the furnace side, and you've got the water coming out on the left-hand side of the drum going down. That's the downcomer. It goes to the header at the bottom, and then the header feeds probably slightly subcooled, maybe saturated. You'd like it to be saturated, but it's probably not completely saturated. That's entering the bottom of the water wall tubes, and then either by forced or natural circulation, it rises through the tube. Some of the water boils off into saturated vapor. It goes to the drum for separation. The steam goes out the top. The once through situation is basically for the supercritical boiler, where this thing shows bubble formation. I think you can have once through boilers that are below the critical point, but I think the vast majority were above the critical point, so that there really isn't a boiling effect. There's just a smooth transition. And I don't really know how else to describe it. But anyway, so that compares and contrasts drum boiler versus once through for steam generation. All right, clockwise, here we go. Okay, so this is my picture to discuss natural versus forced or pump circulation. And so you see on the left, we've got natural circulation, so the downcomer is not heated, so that the water on that side is denser than the water on the heated side, which is, you know, which is the water wall tube side of this thing that's receiving mostly radiant energy from the fireball that causes the water to boil, so the water is hotter, which makes it less dense, and part of the area inside that tube is made up of steam bubbles, and they are far less dense, and so that's that density gradient that causes that natural circulation through the loop. Then on the right, we've got the forced or pump circulation, which you have all of that going on, but you got a pump that's put in there as well to go ahead and give you additional control on it. You can get more bang for the buck out of the pump side, but again, then you got a pump that you got to maintain. They can go down. They can cause maintenance issues. On the natural circulation side, I mean, you know, it's going to pretty well happen. I mean, you do have to get fired up and get that thing circulating. So you got to be a little careful on the startup side that we don't fire too hard until we get this flow established from the drum down the downcomer and up through the water wall tubes. You could overheat a tube if you're not careful. All right. Clockwise. Whoops. Sorry. I'll get there. There we go. Get my clockwise and counterclockwise going. So this is pretty good. This is not, they don't have everything on here, but this kind of shows you a breakdown of the water circuits, the two-phase where you've got water and steam, and the steam circuits, you know, as you come through a fairly simple utility boiler. So let's just trace through here for a second. So we've got the water circuit A, B, C, D. And so I'll give you a little time. I'll do it with the arrow, but I'm not sure the arrow gets captured on the video. But anyway, so A, feed water comes in on the feed water line. So that's where it enters the economizer. Just tubular heat exchanger, has hot flue gases. Actually, they're fairly cool flue gases, but it's still probably 800 degrees, something like that, which is pretty warm to me. Flowing across it. So then feed water enters at A, comes out at B, and then that's back in a pipe. And then from B, we go up to C and over to D. So basically, we're just going to the steam drum. Okay, so that's the feed water path from the last feed water heater into the economizer, out of the economizer, and then it's piped over to the steam drum where it enters, and that maintains drum level and keeps that reservoir of water up at the top of the boiler to make sure that we don't boil those tubes dry, which would be a bad thing. Okay, then we've got the two-phase circuit, D, E, F, G, and H. So D, you're up at the steam drum, and you're going to fall down the downcomer to E, which is a header that then is going to feed the water wall tubes. So from F to G, that's the water wall tubes. So we're really not two-phase down the downcomer, but anyway, that's a little bit of a misnomer. That's just water. There shouldn't be any vapor in that. And also over from E to F is really not two-phase, but from F to G, that's where the steam is generated, and then from G back to D into the drum where we do separation. So that's pretty good. And then it gets a little more complicated. See if I can make my way through this. On the steam circuits, we've got a couple. So let's say, let's do the bottom one first because I said, well, I can go either one. So H is the steam exit from the steam drum. And then as you come around and drop down, if we go left at that first junction, we hit I, uh, I to L. That's cooling the steam path. So those are tubes on the roof and that roof sees very, very hot gases. That's coming right out of the furnace. So that's probably 22, 2,500 degree gases. So that has to be cooled, that enclosure. And so we use some of that heat to start preheating the saturated steam into superheated steam. So that's from I to L. And then from L, we have additional steam cooled enclosure. And so I to L to M. Then M is the primary superheater, which M to N. And then we're going to come out and we're going to go back to O, which is the secondary superheater, which is closer to the drum. And we're going to come out. I guess we go to P, getting this backwards. Where's O? Oh, no. Well, I take it back. O is the attemperator, where we can spray to control steam temperature. And see, we want to go in. We don't want to do that coming out of the boiler because what if that sticks open? We could put water in that, liquid water that could potentially, if something fails, get to the steam turbine, which could damage the steam turbine. So we want to spray in between the superheaters, which is where you see at point O on the attemperator, then to P, which is the entrance to the secondary superheater, and then we come out, I guess, at Q, and then we're in the steam pipe going out to the turbine from Q to R. Okay, I think I made it through. Then there's a slightly different path. If when you come out of the drum at H, you go down to J, and then to K, it's just more cooling. So J to K, MN, OPQR. So it's basically the same thing. So anyway, you should think about that. Think about the other pictures that you've seen, and hopefully that'll give you some kind of an understanding of the flows through the boiler. So I'm not sure how long that's been, but that's probably enough for right now. So I'm going to go ahead and cut this off. I'll send it to you, and then we'll be moving on to some other topics here on the coming lectures. So hope you have a great day, and I'll be back in touch. Bye-bye.